Okay, this is our second video on Turing machines. They're worth it. This is the culmination of the models of computation that we've been talking about in this course. And that is the title of the course as well, Models of Computation. Turing machine is the most powerful model of computation that we have. So I'm going to go through a couple more examples. What we should do is go back and look at this language. This is the language we've studied a while now. This is a great case study language. And you should remember why a DFA and an NFA can't handle this. Go back and make sure you get why this language cannot be recognized by a DFA or an NFA. And then understand why the PDA was able to recognize it. How did we modify the NFA to build a PDA that can recognize this language? And then, now that we have a Turing machine, understand the different way that the Turing machine is able to operate to recognize this language that the PDA can't. And the Turing machine then is able to go on to this next language and add a C to the end. So just briefly to overview this again. What the Turing machine does is different than the PDA. The PDA would take all the A's and put them on the stack and remember them. And then when it gets to the B, it'll pop them all off so that it knows exactly how many A's and how many B's. But then if we would have a C, the PDA is out of luck. It is now lost its memory. It can only access its memory one time. It's like a world where once you've accessed memory, you can't access it again because of the way it's stored on the stack. So every variable you access, basically, you store this n, you retrieve it, and now you can't access it again. Imagine how you would program in that world. It's very limiting. But a Turing machine doesn't behave that way. A Turing machine has the entire infinite long tape, which is its memory, and there's no real difference between the memory component and the inputs themselves. You can overwrite inputs, you can change things, you can move around on this tape. So that's what's happening here with the Turing machine. Instead of counting all the A's and then remembering that, and then counting the number of B's and seeing if the counts are the same, it starts with an A, it marks it with an X, and then it moves over to the right until it finds a B and it marks it with a Y. Then it goes back to the A's, marks it with an X, goes back to the B's, marks it with a Y. And it keeps going back and forth until it either has the same number of X and Y's, until the whole thing is X and Y's, or until one thing's an A without a corresponding B, or one thing's a B without a corresponding A. So in the event that it's not the same number on each side, we're not going to get to the halt state. We only get to this halt state, which means we've recognized the string as part of this language when we have the exact same number of A's and B's. Let's look at another example. We're going to add 4 to a number. These numbers are in binary, so remember what 4 is. It's 1, 0, 0. So that's why the first thing we do is move 2 cells to the left. So this state 0 is the state where we say, let's move 1 to the left. So this means I look for a 0 or a 1. I don't change it at all. I move to the left by 1. So this is state 0, means I moved 1 state to the left, 1 cell to the left. And now I'm in state 1. So now state 1, I'm going to move to the left again. So I have state 1 and state 0 are the moving of the 2 cells to the left. You can imagine if I wanted to add 8 to a number, I would just have 3 move lefts first. If I wanted to add 16 to a number, I would have 4 move lefts first. And then we move add 1. So if it's a 0, then we're going to have a 1 there, right? So now we're changing the number to correspond to the adding. So if there's a 0 and you add 1, you get a 1. If it's a 1, you add 0. You add 1, you get a 0 and a carry. So that's when you go to your carry state. So state 2, you put a 1 in there for that. And then when you find the left end of the string, you just move back and you're done. So if it's a 0, you move left. If it's a 1, it's a move left. Once you find the left end of the string, you just keep moving until you get to the left, and then you get this symbol, which means you're done, and then you move to your halt state. So the real work here is in state 2 with adding the 1 and dealing with the carry state, and then we move on. All right, so now we want to move a string to the left by 1 position. So we're going to say that we end at the left end of a non-empty output string. So start state's going to be 0. So we start here, and then we have to go find the A or the B. So if it's an A, we go to state 1. If it's a B, we go to state 2. So this is now 2 different states. So we're going to start in state 0. If there's nothing, then we're just going to go to state 4, which is our end state. But if there's an A or a B in the string, then we go to state 1 or state 2 appropriately. In state 1, we write the A. and then we move to the right, we move back. If we're in state 2, we write the B, then we move back. And then we skip over. And then where we're at is we go back to 0. And then we'll go write an A or go write a B, 1 to the left. And so as you iterate through this whole process, you end up taking the A's and the B's and moving them 1 spot to the left, 1 cell to the left. And then when you're out of time and when you're done with the whole thing, then you move to state 4 here when you're done. Then you don't have anything left, you move to state 4, and you move all the way to the left to the output, and then you move past all the A's and B's that you've written, and then you halt, and you're done. So in this way, the Turing machine can do something like this, which isn't something that we did with our other automata. With the other automata, we were primarily just recognizing the input of a language, but now the Turing machine can do an algorithm, right? This is an algorithm, right? Move a string 1 to the left. You could imagine this in an array or an array list. You take the inputs and you want to move them all 1 to the left of the index. You want to shift an array, and you would write a for loop to do it. Well, this is what the Turing machine is doing. This Turing machine is programming. We've gone from the DFAs, which were just straight up circles and arrows, to the PDAs, which were circles and arrows that had a little bit of an instruction in them. Now to the Turing machines, which are programs. And this is such a simple kind of program, but it can be shown mathematically that these kinds of programs can emulate any other kind of program that you do. You don't write in this. You wouldn't, as a software developer, use Turing machine programming instructions to build your code. But when you want to actually analyze what the limits of computation are, what kinds of problems can I write Turing machine code for, the claim is going to be that if a problem is amenable to Turing machine code, then that means we can write other programming language code that can solve it. And if we can prove, using all of this stuff here, that no Turing machine can solve the problem, then we're going to conclude that no C++, no Java program can solve the problem either. And that's the get. That's where we get to in this course. That is the fundamental takeaway, that we can use this mathematical formulas to prove whether or not some sort of statement, some sort of problem statement, is amenable to a C++ or a Java solution. This can help us because then we can say, okay, here's a problem that I want to try to solve, and maybe it can be solved. So then I just don't want to try, right? I'll try to find an approximate solution, or I'll try to transform the problem in a way that's slightly different that I can solve and still have value. This is why we can think about this, the science of computation, the science of computing, the science of algorithms. This doesn't help you in a practical sense at your software engineering job at Cerner, but this helps you understand the breadth of the field. When we talk about studying the science of computing, when we talk about algorithms as abstract Platonic forms, this is what we're dealing with. This is the limit of what computers can do. If you want to write dystopian science fiction or something, you can say, what can the computers do? What can the AIs do? What can robots think about? And how is that different than what people can think about? If you're going to say that you're limited to a Turing machine. Turing machines can't solve everything. There are certain types of things you can write up here that maybe aren't amenable to a Turing machine solution. Here's different ways we can think about it. You can have a one-way tape where you can only go one direction. You can have multi-head Turing machines where you can be looking at two different things at the same time. You can have multi-tape Turing machines. These are all equivalent. They just have some benefits in terms of how easy it might be to write programs for certain applications, but they're fundamentally all the same. And non-deterministic TMs have the same power as deterministic Turing machines. So we basically say the Turing machine is it. It is the most powerful thing that we have.